Hello, today we are going to tackle topic 8.4. I need you to prepare yourself a little bit. This is a longer topic. It does have some detail work to it. Take your notes carefully, take a pause if you need to, and you can always pause and practice some of the things and come back to the rest of the notes if you need to. So let's just review what we've learned so far in Unit 8. We have taken a look at significant figures for pH, so we want to keep that in mind as we do things. So your significant figures of your concentration, so if it has 2 sig figs, that's going to tell us our number of decimal places on pH or pOH. So 2 sig figs is 2 decimal places, 1 sig fig is 1 decimal place, etc. So here's an example. We've got 2 significant figures in this concentration. Then our pH, when we take the negative log, is going to be 3.92. So that has 2 decimal places. So those are our significant figures. All right, in topic 8.2, after learning about pH and pOH and how we can convert between those different values, we looked at finding pH and pOH of a strong acid by itself or a strong base by itself. For strong acids, they react with our water and give off their hydrogen, forming hydronium and their conjugate base. And your concentration of your strong acid is going to equal the concentration of each ion. For example, if I had a 0.5 molar HCl solution, then my hydrogen or hydronium ion would be 0.5 molar and my chlorine ion would be 0.5 molar because it's a 1-to-1 ratio. And then pH can be calculated from that hydronium ion or hydrogen ion. So we take the negative log because P screams at us, take the negative log. And we do that and we get a pH of 0.3. So we can see that's a very low pH. That's very acidic on our pH scale. We can do the same type of thing with a base, strong base alone. Again, we can see how it dissociates in water in an aqueous solution and will completely dissociate. Notice that our arrows on both of these are not equilibrium. They're going in one direction. So again, your concentration of your base is the concentration of each ion. Same idea, 0.5 molar for the whole solution would be a 1-to-1 ratio with our ions. So 0.5 molar for either or for both. Now, since we have a hydroxide ion concentration, we could find pOH from that concentration. So we take the negative log and we get 0.3. Notice, doesn't matter which chemical it is, right? If we're taking the negative log of 0.5, we're going to get the same answer. But our pH, we calculate from our pOH. We do 14 minus that pOH, and we get a pH of 11.70. So these are on opposite ends of our pH scale. Very acidic over here, very basic over here. Now, one thing we need to watch out for is our group 2 metals for our bases. So if it's a group 2 metal and you have a formula like CaOH2, then you have to consider the mole ratio. Okay, for example, calcium hydroxide would break into 1 calcium and 2 hydroxide ion. So we're getting twice as much. So our concentrations need to follow that mole ratio. Again, if we had a 0.5 molar solution, then calcium would be 0.5 molar and hydroxide would be 0.5 molar. Since it, I don't know what this is there, since it is a 1.2 or 1-to-2 mole ratio. So then we would use this to find our pOH and then our pH. All right. After that, in topic 8.3, we took this a step further and started looking at weak acids and weak bases. Now, weak acids and weak bases are a little bit different. They are going to create an equilibrium. So what distinguishes a weak acid from a strong acid is that they only partially ionize, right? We aren't going to break fully apart. So we're actually going to get an equilibrium. And I forgot to put that arrow there. So the ionization reaction of weak acid is shown like this. So we take our weak acid. HA is kind of the generic form of a weak acid. We'll see that on our equation sheet as well. We add water, and we're still going to get hydronium and then our conjugate base, right? When we lose a hydrogen, we get our conjugate base. But this creates an equilibrium. It's not one directional. Our equilibrium constant expression, we can create that, again, given on your equation sheet. We've got our Ka, so the equilibrium constant for our acid. And again, these are for weak acids. The value here would be so big because we wouldn't have any of this left for a strong acid. It's like dividing by 0, right? It's going to be so big that we can't even really measure this. So sometimes on tables, they're listed just very large numbers. They don't even give you a value. So these are for weak acids. We've got our products concentrations divided by our reactants. We leave out the water because it's a liquid. And then we can actually solve this, right? If we wanted to do an example, if we're given the concentration of the acid, of our weak acid, and our Ka value, we can use a Rice table with X values in it to determine the concentration of each ion at equilibrium. So if we have it says a synthesis or a solution of HF, remember HF is that tricky one. We feel like it should be strong, but it is weak. It has a Ka of 1.6 times 10 to the negative 4 and a concentration of 0.5 molar. So we've put our molarity in there. We start with 0 of our products as usual. We cross out our liquid water. And then we're going to use X values. Everything's a 1-to-1, so we're going to subtract X here, add on the right side, and we get 0.5 minus X, and then our X values. Now we do make the assumption, like we've done before, that this X is going to be so small because our value here is small that we're going to get just 0.5 there. And then we're going to plug in that equilibrium line like we've done many times before into our Ka expression. So we'd plug in the X and the 0.5 and our Ka value 1.6 times 10 to the negative 4, and we would solve for X. If we did that and went ahead and did that math, you can go ahead and try it. This would be a good place to practice that. We should get an X value of 2.8 times 10 to the negative 3. So that means both of these ion concentrations are that value, right? Because they're equal to X. So we can report that. And then we can calculate a pH from there. The pH is going to be calculated from your hydronium ion or hydrogen ion, right? They're interchangeable. So negative log of that is going to give us 2.55. So acidic, still pretty low on the acid scale, but not as low as a strong acid like we got before with a 0.3. Doing this with a weak base is very, very similar, right? Again, it only partially dissociates or partially ionizes. Again, we should have a double arrow there. I'll fix that on the official version. And we can get our equilibrium constant expression. So we've got a base, a weak base plus water. Bases take hydrogen. So we're going to take that hydrogen from the water, become positive. And then what's left of water is OH. Remember that another way we can think about water is being HOH, right? So you've got the hydrogen ion and then the hydroxide ion. So your positive one goes to the base and your negative hydroxide is left alone by itself. Now, same process. We've got our equilibrium constant. If we were given concentration of the base and its Kb value, right? Ooh, another typo I need to check. Sorry, Kb value. We would use our Rice table and X values to calculate. So if we had NH3, that's a weak base. NH3 can gain a hydrogen and become ammonia or ammonium, and then leave the hydroxide, so we get that basic solution. And we have a Kb of 1.8 times 10 to the negative 5. So we could do the same setup in our Rice table as we saw before. Again, solving for our X value, if we plug in these values into our equilibrium expression, we can solve for X, and we get 3.0 times 10 to the negative 3. So our hydroxide and ammonium concentrations are both 3.0 times 10 to the negative 3. And then because we have hydroxide, if we do negative log, that's going to give us our POH. So we can go ahead and calculate that. Negative log of our concentration gives us 2.52. But then we would subtract from 14 to get our pH. So that takes one more step than we did at the acids, but it gets us our So now we're going to take this a step further. We have looked at strong and weak acids and bases all alone by themselves and seen what kind of equilibrium or what kind of situation we have when they're alone. Now we're going to see what happens at various points in a chemical reaction involving strong and weak acids and bases. So we're going to start mixing things together, and this is where we can get a little more involved. We're going to start with a strong acid and a strong base. Okay, so something we want to do when we first approach a question like this is we want to decide, is our acid and our base that we're given, are they strong or weak? Let's see if I can focus this a little more. Okay, so there's a couple of pointers, couple of things at the top to get us started, and then we'll get into an example. So a strong acid reacting with a strong base will always have the net ionic equation here. So our strong acid would separate into its ions, and it'd give off its hydrogen, right? It'd release that hydrogen. A strong base would separate into its ions, and we get hydroxide, and we would make water and typically a salt of the spectator ions. The salt would be soluble, so they would all be spectators. So we'll see an example of that down here with sodium hydroxide and hydrochloric acid. The pH at the equivalence point for this, so we're going to talk titrations as we go. Remember, a titration is where we're adding slowly one chemical to another to react them and try and get to that middle point, that equivalence point where they have equal moles of chemical, right? So our equivalence point is equal moles, all right? So the pH at the equivalence point, because we have a strong acid and a strong base, they meet in the middle on our pH scale. So we get a pH of 7. So that's a really handy thing to know. And when we start to get into our next topic, where we start to look at the graphs of titrations, that's going to really help us to identify if it's a strong or weak acid and base. All right, the pH of a mixture of strong acid and strong base in any other mixture, so if they're not equal moles, we can determine from the concentration of the excess reactant. A BSA table can help in this calculation, but we don't really have to do that every time. There's going to be a little bit, we can kind of shorten that. We don't have to do all the steps of a BSA table because we're really only looking for the chemical that's in excess. So let's just take a look at one of these reactions. We've got 25 milliliters of 0.5 molar NaOH added to 10 milliliters of 0.5 molar HCl. So we can recognize we have equal molarity, but we do not have equal volume. If we had equal molarity and equal volume, everything's going to be equal. We're going to have equal moles. We're going to be at the equivalence point. We're at a pH of 7. Right? We don't even have to we shouldn't even have to think too much about it. But we want to know the pH of this solution. So we're going to first determine the moles of each chemical that's reacting. Now I want to show you the net ionic equation for this real quick. So if we had NaOH and HCl, both are aqueous. When an acid and a base react, we're going to take that hydrogen and hydroxide, and those are going to be our water. And we got sodium and we got chlorine. We make sodium chloride. So this would separate into its ions. This would separate into its ions, again, because they're both strong. Weak stay together, strong and independent and separate. And sodium chloride is soluble because it's got that group 1 ion. And so they would separate. Plus salt, sodium chloride, definitely dissolves in water. So when these all dissolve, the sodiums are going to be spectators and the chlorines are going to be spectators. So you get that hydrogen ion, that hydroxide ion, and you get water. Because it's a liquid, it stays together. So that's why we get this same net ionic equation every time we mix a strong acid and strong base. So that's a nice thing about these. Okay, so we're going to first determine our moles of each chemical that's reacting. So I'm going to start with my NaOH. I've got 25 milliliters, so 0.0250 liters times 0.50 molar solution. And when we do the math there, I got my cheat sheet over here. Where's my strong acid, strong base? There we go. We are going to get 0.12 0.0125 moles of NaOH. So there's our moles of that one. We're going to do the same calculation but for HCl. So we've got 0.01 liters, same molarity, and we are going to get 0.0050 moles of HCl. Okay. Now we're going to determine the excess reactant and how much is left over. So an acid and a base, strong acid, strong base, are going to neutralize each other, meaning they're going to react with each other and make water. So we want to see which one's going to come out on top, which one are going to have excess of. Well, it's the one that's bigger, right? That we have more moles of. So 0.0125 is bigger than 0.0050. So we're going to go ahead and we can see that the moles of NaOH are larger, so it will be our excess, which means the other one is our limiting reactant. Since they're a 1-to-1 ratio, we can just subtract the values and determine the excess moles. When we've done BSA tables before, that shift line deals with or is based off of mole ratios, but our mole ratio is 1-to-1, so it makes everything easier here. So we're going to take our 0.0125 moles, and we're going to go ahead and subtract our 0.0050 moles and see how much we have left over. So when we do that, we get 0.0075 moles of NaOH left over. So the part that we subtracted the same amount. So 0.005 moles of the acid reacted with 0.005 moles of base. That's gone. Those are no longer in the solution. We've now created water with those and our salt. But we still have sodium hydroxide left. Okay. Now, once we have that left over, that's the main thing that's changing our pH in the solution. This is what's controlling the pH now. So we're going to use the excess moles and our total volume of the reaction to determine the molarity of the excess. So when we pour these together, they're diluting each other. We've got water from one and water from the other that are mixing, so we have a total volume that we're dealing with. So we want to take our moles of our sodium hydroxide, and we're going to divide it by our total volume, okay? Total volume. Well, what's our total volume? Let's look up here. We've got 0.025 liters and 0.01 liters. We're going to add those together, 0.0350 liters, and find our new molarity, which ends up being 0.214 molar sodium hydroxide. Now, this is a strong base. This is exactly what we were looking at when we were looking up here at our strong bases alone. So if we know the concentration of our strong base, then it's a 1-to-1 ratio for each ion. And so we can use that value to find our pOH. Okay, so we're going to calculate the pH or pOH based on the excess molarity. Since this is its sodium hydroxide, we're going to find pOH if we take the negative log. So since NaOH is in excess, taking the negative log will give us pOH. So negative log of 0.214 gives us our pOH. When we do that, we get 0.670. But let's check our question. We are determining what the pH of the resulting solution is. Oops. Oh yeah. And so we're going to go ahead and calculate that, but we've learned we can relate these together. 14 minus 0.670 is going to give us 13.330. And that is our final answer. So with a strong acid and strong base, it's actually pretty straightforward. The main thing is that we need to figure out who's left over, who's in excess. And that's the one that's going to control that pH of our solution. So once we figure out moles of each, we can subtract our moles. You do need to find moles first. You can't just subtract molarities. Remember, that's just a piece of things. We got to figure out how much is in that solution. If I've only measured 10 milliliters of 0.5, I've got a different amount of moles. So we got to make sure we're in moles. subtract those values, figure out who's left over, find its new molarity once it's been diluted by divided by the total volume, and then we can find our pH and pOH. If our acid is in excess, then when we get down here, we go straight from, we just get our pH. We don't have to do a negative log and then subtract, because when we take the negative log of an acid, we're going to have pH. So that one's a little bit easier when you've got that going on. So doesn't matter with our strong acid, strong base, as long as one of them's in excess, this is going to be the same pattern we follow. The only time it's different is when they're at their equivalence point. When they are equal moles, then we know our pH is 7. Shortcut. Okay, so we could just say it. If we needed to justify our answer, we could just say it is at the equivalence point, they're equal moles of acid and base, therefore the pH is 7. Okay, now we're going to take a look at what happens when one of the solutions is weak. We're going to start with having a weak acid and a strong base. Okay, this is going to be a little more involved. Okay, so if you need to take a break, this would be a good time to do it and then come back. So we're going to start with a couple of points. So a weak acid reacting with a strong base will have a net ionic equation here. So your weak acid has that general formula of HA, whatever that acid part is, with that hydrogen in front, and it doesn't dissociate. It doesn't break up because it's weak. Weak ones stay together. Our strong base would break up, so we get rid of that spectator ion, and that's why we don't have a second ion here. So these two would have the matching spectator ion. We've got our hydroxide. So our acid gives away its hydrogen. It still reacts, even though it's weak, and we make water. And then we get our conjugate base. So there's different points where we're going to have to make different calculations. Okay, so if the weak acid is in excess, we're going to look at that. We have if the volume added is half the volume needed for the equivalence point. So if the volume added of strong base is half the volume needed for the equivalence point, we're going to see what happens there. Looking ahead, we're going to see if they are equal molar. So what happens when they're at the equivalence point. Okay. If you were faced with one, and these are rarely pop up, I've actually never seen them as an example, where the strong base is in excess, then we just kind of treat it just like we do strong acid, strong base. We figure out how much is reacted. The strong base is in excess, has leftovers, and we go from there. So we've done that part already. So if our weak acid is in excess, it creates what's called a buffer solution. So a buffer is where we have a weak acid in solution and its conjugate base. Okay? When both of those are in solution, so weak acid and its conjugate base, then we can use this equation to determine the hydrogen ion concentration, and therefore we can use it to find our pH. So a buffer solution is a solution that kind of resists that change in pH. We're going to be looking at what are called titration curves in the next section, and we're going to see on the actual graph where our graph starts to kind of, it inches up really slow instead of having a drastic increase. So we create a buffer solution. We're going to learn more and more about buffers as we go through the unit, and we'll see this equation pop up. But if we have a weak acid and its conjugate base, then we can use this equation. So let's see one. HCN is a weak acid with a Ka value, 6.2 times 10 to the negative 10. If 50 milliliters of 0.1 molar HCN is titrated with 0.1 molar NaOH, calculate the pH of the solution after 8 milliliters of the NaOH has been added. So we've got 50 milliliters of 0.1 molar, we've got 8 milliliters of 0.1 molar. So we can see that we've got equal molarities, so our volume here is in excess. We've got excess weak acid, so that's going to be where we can use this equation. So let's try it out. We are looking for our hydrogen ion concentration. It's equal to our Ka value. Now I will point this out. This is not on your equation sheet. This is a little secret equation, but it's going to make our lives a lot easier. Okay, this is instead of doing a bunch of rice tables, we're going to just use this equation a lot. All right, so we are going to take that and we're going to plug in, so I need my little cheat sheet over here where I've got everything written out. Our, we want our moles of our acid over our moles of our base. Okay, so our moles of our acid, we take our volume, 0.0500 liters times our 0.100 molar. And we're going to get 0.0050 moles of our acid. Okay, so that's our acid that we have present to start with. And to start with, we don't have any base present. Okay, so the main thing that's in the solution in our container is our HCN. Okay, now what we're going to do is add or subtract a value for our base. Now we're going to do that because it's kind of like our rice table, right? So our base is being added to our acid. Okay, so if we imagine our titration, our reaction, we've got our acid in our container, we've got our base being dripped into it. Okay, so it's like the base is invading into the acid. So we're going to add or subtract our invader. Well, we're adding base. We've got 8 milliliters of 0.1 mol or 0.1 molar solution. So we are going to again multiply those to get our moles. So it ends up being 0.0008 moles of base that's invading into our solution. So that means that part of this, I wasn't supposed to put a negative there, or a positive. That's a negative. So part of our acid's going to react that same amount of moles. Okay. So let's take a look. We've got our amount of moles of acid to start. That's in our container. We're dripping base into our acid. So part of that acid is going to neutralize. So we're going to subtract our amount of base. And our amount of base that's reacted, we're going to add on the bottom. So we're going to get a new ratio here. Okay, so if I was to simplify this and do the math, we'd subtract these, we'd add this one, and we'd do our multiplication. We should end up with 3.255. I'm going to keep my sig figs for a second. Keep all the digits. 255 times 10 to the negative 9, because we got to do one more step. We're going to find our pH. We still only have 2 sig figs, and we can make that note up here. So our pH is going to have 2 decimals places. Once you have your hydrogen ion concentration, this would be a molarity, we can take the negative log. Since it's hydrogen, when we take the negative log, we're going to get pH. And our value, when we take the negative log, is 8.49. So that is our, did I get that right? Yes, 8.49. So that is our pH of our solution. Okay. Okay, I had to pause for a second and fix something. Okay. So that's our pH of our solution. So if we start with our acid in our container, our acid is weak. We're going to already have a pretty high pH. And then we're adding strong base to it. So it's going to shift our pH up towards that base. And so we end up with a basic solution here. So this is a way, if our weak acid is in excess, so that's weak acid is in excess, that we can find our pH of that. Now, there's another special point that happens during a titration where we add, if the volume added of the strong base is half the volume needed for the equivalence point, then the pH is determined from pKa. Okay, well, what would that mean? Well, if we've got 50 milliliters of acid, then it would take, and if they're equal molarity, it would take 50 milliliters of base for the equivalence point. Okay, it would take equal amounts for the equivalence point. So there is a special point that happens when we haven't added 50 milliliters, but we've only added 25 milliliters. Okay, and this creates kind of another buffer situation where we have weak acid. Okay, we've got our weak acid, it's already present, and then we've reacted half of it. And when we react half of it, we've got an equal amount of conjugate base. Okay, because we've added 25 milliliters of the base to react with it. So we've got equal amounts of weak acid and its conjugate base. When that happens, we have equal concentrations, equal moles of acid and base. So this whole term here, if we were to use this equation, so we look at it, we get H plus equals Ka, and we got our acid over our base. Well, if these are equal, then this whole term becomes a big old 1. Okay, so that term doesn't matter. We got hydrogen ion equals the Ka value. Well, if we take the P of this, we get pH, and we take the P of this, we get something called pKa. Well, what are we doing when we take the P? We're doing the negative log. Okay, so this is a shortcut. Love this shortcut. So it says in the same reaction above, 25 milliliters of sodium hydroxide is added to 50 milliliters of HCN. What's the pH of the solution? Okay, so we notice that we've got that's the equal molarity, 1 to 1, or 0.1 to 0.1. We've got half the volume going on. So we haven't gotten to our equivalence point, but we're halfway there. So we can say that the pH equals the pKa of the acid. Well, what do? pH equals the negative log of our Ka value. That's what the P stands for. So negative log, our Ka value we have given up here, 6.2 times 10 to the negative 10. So our pH is going to equal 9.21. So we can see our pH is inching up. We've gone up another whole pH unit because we've added more base, right? When we add more base, our pH is going to go up as we go. So that's the lovely one. So far, we've gotten away with doing no rice tables, reacting weak acid and a strong base. Lots of teachers teach it with lots of rice tables, so we're saving ourselves. Okay, so let's look at the next chunk. Here's where you can see we do get a rice table, okay? So if they are equal molar, okay, as the equivalent or as at the equivalence point. So when we reach the equivalence point, then you are calculating the pH of a salt. Okay, what do we mean by that? Well, when our weak acid reacts with our strong base, we're making water. And we're making that conjugate base. Well, this technically also has whatever spectator ion is on that base. So if this is NaOH, this would be Na with that conjugate acid ion. So if this is HF, then this would be NaF, right? We're creating that salt. This is our salt. So we can say the acid and the salt of the weak acid, or the salt, goodness, this is our weak acid and its conjugate salt, essentially. Okay, conjugate base. So we're going to write a reaction, write the salt hydrolysis reaction. So the problem is that this salt reacts with water and we get another little side reaction, which is annoying, but it does happen. So we have to write a new reaction. And this is probably the ugliest part. I think this is the ugliest and hardest part of AP Chem. But don't let it scare you because we can work through it, okay? So we got steps. So we're going to write a salt hydrolysis reaction. We're going to complete a rice table and solve for X. We've done that before. Again, everything's going to be 1 to 1. Since the base is strong, the solution will be basic, and you will solve for the hydroxide ion. Then we can find POH and pH, okay? So we got to think about what's strong, what's weak, and that's going to help us through this. So in the same reaction above, so we're dealing with the same chemicals, same molarity. So 50 milliliters of our base is added to 50 milliliters of our acid. We are at the equivalence point. Okay, what is the pH of the solution? The solution has strong base. Okay, the solution has a strong base. So the acid's conjugate base, this one over here, will react with water to form hydroxide. So that's the first thing. When we're writing our hydrolysis reactions, I'm going to start with my arrow and I'm going to say, okay, I've got a strong base, so I'm going to create hydroxide. Okay. Then I know that my acid was HCN. Well, if I get rid of my H, then I've got CN reacting. It's always going to react with water. This is not going to change. So what are we left with? Well, if this creates hydroxide, that means a hydrogen transferred over. So we're going to get HCN. Okay, so that's how we build this thing. We go, okay, what's strong? If it's a strong base, we're going to put hydroxide. If it's a strong acid, we're going to put hydrogen. Okay. And then we're going to go from there. We're going to say, okay, what's our conjugate? We're going to write that with water and then see what it does. Okay, to finish out the reaction, balance it out. So what do we need to do first? When we do this, because these are equivalent, our moles of our acid are equal to our moles of our base, which are also equal to the moles of the salt formed. So if we find moles of one of those pieces, we will have the moles of our chemical. Okay, so I'm just going to pick my acid because that's what I got. So my moles of my acid, find my cheat sheet here, too many pages. There we go. So my moles of my acid are 0.050 liters times our molarity, 0.100 molar. And so we get 0.0050 moles. So that's our moles of our acid are equal to our moles of our salt. Okay, so equal moles of salt, which is this part. Okay, so we got our moles of that. Now, again, we have poured things together. We've changed their molarity, so we need to find our new molarity. Again, moles over the total volume. So that part is consistent. Keeping track of your total volume is nice in these kinds of things. So our total volume, we got 50 milliliters and 50 milliliters, so we got 100 milliliters, so 0.100 liters. So when we divide that, we get 0.050 molar solution. And that's our initial concentration of that salt. Okay. Salts of our conjugate base. We're going to have none of the other chemical. So this is, we're doing our titration, everything's good, and then this like little side reaction happens, right? So that's what we're calculating here. We do our rice table. We're going to do our standard little subtract x, add x situation. And again, this we can assume our our Ka from our previous page was 6.2 times 10 to the negative 10. That is super tiny. Our x is going to be extra tiny. So we're going to say this is just 0.050. We're going to plug this equilibrium line into our Kb expression. Okay, yes, it's Kb. This is a basic solution. So we need Kb. So we're going to do a little side calculation here. What's Kb? Well, Kb we can get from this equation. Ka times Kb equals Kw. How convenient is that? We've seen this in another way in terms of Kw equaling our hydrogen times our hydroxide. So we can divide by Ka and we get Kb. So Kw 1 times 10 to the negative 14th divided by our Ka 6.2 times 10 to the negative 10. And so our Kb value is 1.6 times 10 to the negative 5. So we're going to plug in. So our Kb would be, expression would be hydroxide, HCN over our Cn minus. We can plug in. So we get 1.6 times 10 to the negative 5 equals, we got x and x, so x squared on the top, and 0.050 on the bottom. We multiply this over, so x squared, I don't have this all steps worked out. So 1.6 times 10 to the negative 5, we do that calculation, times 0.05. 8 times 10 to the negative 7. And we'll square root it. So square root of the answer, 8.9 times 10 to the negative 4. Is our x value. So that means these two concentrations will equal 8.9 times 10 to the negative 4 molar. Since we have our hydroxide ion concentration, we can find our pOH. Negative log of that would be negative log of 8.9 times 10 to the negative 4. So negative log 8.9, 10 to the negative 4. And no, we're good, 3.05. So pOH equals 3.05. But we want pH, so we're going to do 14 minus 3.05. Don't trust my subtraction right now. I'm too sleepy for that. It's very early in the morning. So we get 10.95. All right. So there is our calculation for when we were at our equivalence point. So this one's more involved, right? Which is kind of stinky. It's not great. But remember, you don't even have to do a calculation when it's strong and strong. So we kind of get away with not having to do anything when it's both strong. So we have to do a little extra work when one of them's weak. Okay? So let's just review what we did here. We've got the equivalence point. We got equal molarity. We got equal volumes. When that happens, we're going to get a side reaction that occurs where the salt that we form is going to do its own reaction. It's going to react with water. That's why we call it the hydrolysis reaction. That hydro part means water. So we're going to react that conjugate with water. Because we have a strong base, we know it's going to be a basic solution. And then, so if this creates hydroxide, that means the water gave away its hydrogen, we get HCN. Okay, so we're taking the conjugate base and creating an acid from it. Right? We find its concentration, its initial concentration, because our moles are all equal now. So we find the moles of one of our chemicals, and we divide by the new volume to get its new molarity. We set up our rice table with x's, very standard rice table at this point. When we plug in, because this is a basic solution, because we've got a strong base, we're going to use a Kb value. To find our Kb, we can do a little side calculation with Kw. This is on your equation sheet. And we can find the Kb, plug everything in and solve for x. That gives us our hydroxide ion concentration from our rice table. And then from there we can find pOH and pH. All right? So that one took a little bit of time. I know that weak acid, weak base takes a little bit more time. So we've got 3 different points that we can calculate. We can say when our weak acid is in excess, when we're at half the equivalence point, and then when we're at the equivalence point. Again, they typically don't ask for after the equivalence point when our strong base is in excess, but if they do, we treat it like the strong acid, strong base ones. You got strong base in excess, you figure out how much is in excess and calculate your pOH and pH. We're going to do another one of these, but with a strong base, but with a weak base and a strong acid. We're going to see how things kind of shift a little bit when we switch them up. Again, this is a little longer, so take a break if you need to. Maybe find a question that has a strong acid and a weak acid and a strong base, and maybe try that one out and then come back to your notes. Okay, so I have to get my hand brace. All right, so we've got a weak base and a strong acid. So let's take a look at what's our 2 bullet points here. A weak base reacting with a strong acid will have the net ionic equation. So this is the generic form of our weak base. We're going to react it with our strong acid. That acid creates hydrogen or gives away hydrogen, so we get that hydronium ion. And it's going to create that conjugate acid and then water. So we can also look at this in terms of our actual chemicals that are reacting. In this case, we've got NaOH is our weak acid, and then we're going to be reacting it with HCl. So let's just look at that reaction real quick, just so we can see the whole thing. I didn't do this on the other one, but I want to see it here. So we got NH3 and HCl. That acid is going to give away its hydrogen to our base. NH4 plus is going to be created, and then what's left over is our Cl minus here. Okay, so if we were to break these up, NH3 stays together. This would break apart into its ions, and our hydrogen would really be the part that's reacting. So we get NH4 plus from that. So they typically bring in the water here so we can see better what's happening. So this would create our hydronium ion, and then we'd have that water really left over from that. Okay. So if our weak base is in excess, so it's going to be our first one, we're going to look at the same 3 points we did for the other one. So we're going to start with our weak one being in excess. Again, that creates a buffer solution with hydrogen ion, or it both creates a buffer solution, and hydrogen ion concentration can be determined from our fancy equation here. So hydrogen equals Ka times our acid over our base. So NH3 is a weak acid with a weak base. Fixing my typos here. Yours will be right. With a Kb of 1.8 times 10 to the negative 5. If 50 milliliters of 0.1 molar NH3 is titrated with 0.1 molar HCl, calculate the pH of the solution after 8 milliliters of the 0.1 molar HCl has been added. So we've got 15 milliliters of 0.1 molar and 8 milliliters of 0.1 molar. So we've got excess weak base with our strong acid. So first we're going to find, we want to use this equation. I don't want to have to rearrange this and figure out Kb and figure out what changes about this. We don't want to have to do all that. We're just going to switch it to a Ka. All right, so we know Kw is Ka times Kb. So if I want Ka, I'm going to do Kw over Kb. Kw will always be on the top. And then we got 1.8 times 10 to the negative 5. So we get 5.6 times 10 to the negative 10. It's a good place to practice in your calculator too. And then we're going to plug into this equation. So our hydrogen ion concentration is going to be equal to the 5.6 times 10 to the negative 10 times our acid over our base. Now, this is where we got to think about what's happening. So in the container, it says NH3 is titrated. So in our container, we have our base. We are adding to it from our burette our acid, dripping it in. Okay, so we've got base to start with, and our base, we got 50 milliliters of 0.1 molar, so 0.0050 moles. Okay, we're going to do this all in moles. Everything in this thing here is going to be moles. The reason we can use moles, by the way, and not molarity, is because they're both over the same total volume, so those volumes would cancel if we're dividing them. Okay, well, we start out with no acid in our container, right, in our titration. We only have base, and then we add acid, so it's going to add to the acid side and subtract from the base, because some of that base is going to react, so we're going to subtract from it. Well, how much? 8 milliliters of 0.1 molar, so that is 0.0008 moles. And then we can calculate. Try that in your calculator, and you should, theoretically, get 1.1 times 10 to the negative 10. So try it out. Make sure you get that number. Now, this is a hydrogen ion concentration. Well, we want pH, so we can take the negative log of that. So negative log of 1.1 times 10 to the negative 10. And we get 9.96. 9.96. Okay. So, again, creating a buffer solution when our weak one is in excess. So we got more weak base than we do our strong acid. So we're going to create that buffer. We're going to plug into our equation. Since we're given a KB, we're going to switch it to Ka. And we figure out who's in the container to start. We've got base to start, no acid. Then we're adding acid, so it reacts with the base, and we subtract part of it. And that's our invader, right? Our acid is invading our base. So we're going to add our invader and subtract from our base. And we can find our pH from there. Now again, if the volume added is half the volume needed for the equivalence point, then pH is determined from pKa. Well, we've got 50 milliliters of our base, so we would need 50 milliliters of our acid at the equivalence point. So half of that would be 25 milliliters, and that would create this situation. So in the same reaction, 25 milliliters of acid is added to 50 milliliters of base. We got half that equivalence point. So we can determine pH from the pKa. So at this point, pH equals pKa. Again, remember, if we were to plug into this whole term, because we've got equal, we would have 50 minus 20, or we would have our 0.05, and then we subtract 0.0025. This side would add 0.0025, so this whole term would be equal. It would be 1. So our pH equals the negative log of our Ka value, which we calculated to be 5.6 times 10 to the negative 10. And that gives us 9.25. Okay, we can see when we add more acid, we're becoming more acidic. We're dropping in our pH. Okay, we go from adding 8 milliliters of acid to 25 milliliters of acid. And we drop our pH. All right, now for the fun part. All right, our rice table. So, if they are equal molar, as at the equivalence point, you're calculating the pH of a salt. So let's look at our reaction. I just moved my paper. So we are creating the salt of our acid. So basically this NH4 and Cl, that would be our salt. But they dissolve the chlorine as a spectator ion, so we really don't see it. It's the NH4 plus that's reacting. Okay, that's the part of the salt that we're looking at. Okay, so again, if we wanted to write the reaction, we'd say, okay, I know NH4 is my part that's reacting. It's going to react always with water. And our strong thing in this situation is our acid. So we're going to create an acidic solution. That means we're going to create hydrogen ion. So what's left over? Well, if this reacts with this to create a hydrogen ion, well, actually hydronium. Let's do H3O plus because that's really what we're creating. So we're giving that hydrogen to water, and so we get that NH3. Kind of reversing our reaction a little bit. Well, I guess this is another way of writing it. It's just NH4OH. Yeah, I guess I wrote it this way. Okay, well, let's look at it that way. So we'd have NH4 plus our water. We know it's acidic, so we create hydrogen ion, and then the OH goes with our NH4. Okay, so the hydrogen is kicked out, the OH pairs with that. All right, we'll ignore this. Okay, so same reaction above. Oh, let's read through this. So write the salt hydrolysis reaction. We've got that. And complete the rice table and solve for X. And there's some practice on just writing these hydrolysis reactions in your practice. Since the acid is strong, the solution will be acidic. That's why we get this. This makes it acidic. And you will solve for the hydronium ion then you can find pH or hydrogen ion. Okay, so we got 50 milliliters of HCl, 50 milliliters of NH3. We know they're equal molar, so we're at the equivalence point. What's pH of the solution? Okay, strong acid, so the base's conjugate will react with water to form hydrogen and the resulting base. Moles of acid equal moles of base equal moles of salt. Everything's equal. So I'm just going to pick my acid. I just always pick my acid. I don't know why. So we've got 0.0500 liters times our 0.01 molar, 0.0050 moles. So we're going to take that and divide by our total volume. We've got 50 and 50, so 0.100 liters. So we get 0.050 molar solution. We're going to subtract and add x. So we get x and 0.050 minus x. And let's look at our K value. Okay, and this time we are using, let's see. This is acidic, so we're going to use Ka. Our Ka value we already found. It's 5.6 times 10 to the negative 10. That's super tiny. Our x values are going to be way tiny, so this can be assumed to be 0.050. Pretty much you can always bet on that. Okay, we're going to plug this into our Ka expression. We've already got our Ka value, but let's look at our expression. H plus NH4OH over NH4 plus. So we get our expression over here. Let's see, our Ka we found earlier to be 5.6 times 10 to the negative 10. And that's going to equal our two values are x squared over 0.050. And if we solve for x, take a minute and just solve for x, okay? Your x value should be, where's my x value? 5.3 times 10 to the negative 6. Okay, so you multiply this over and square root it. We've done this many times. Should be able to get there. So that value, that x, is equal to both of these. So 5.3 times 10 to the negative 6 molar is the concentration of each of those. We've got a hydrogen ion concentration, so we can find a pH. Negative log of 5.3 times 10 to the negative 6 gives us 5.27. Now we can see we have a drastic change in our pH. We went, when we started, only 8 milliliters of acid added. We were at 8.49. We added, oh, am I looking at the wrong? Nope, looking at the wrong one. Sorry. Okay. 8 milliliters of acid, strong acid, we were at 9.96. We added more strong acid, we dropped to 9.25. We add more strong acid to reach our equivalence point, and is 5.27. Notice it is on the acidic side because we have a strong acid. Okay, when we did it earlier and we had a strong base, we ended on the basic side. Imagine that. There are patterns. So, I know this has taken a while. This is almost an hour-long video. I get it. It's a long one. Told you guys. So, key things to notice. Before you start calculating, you need to ask yourself some questions. Okay? Are the acid and the base strong or weak? Ask yourself. Label them. Know that. Because that's going to determine the path you take. Is one chemical in excess? Okay? Is that chemical, if they're both strong, that tells you which one is your limiting and your excess, what's going to be, how to proceed from there. If it's weak and strong, then your chemical in excess is probably going to be your weak one, and that's going to determine where you're at. Is it at the equivalence point? Or is it at half the equivalence point? Okay, all of these will help determine the path that you take. You've got to ask yourself those questions. You got to know which path you're taking before you set down the path, because you don't want to try and change paths in the middle. All right, so hopefully this helps. This gives you a nice organized way to look at things, to practice, and let's ask some questions in class. Let's get some help. You guys got this.